What you should know about quantum physics, 10 mind-boggling facts. 1. The quantum world is complicated. Can you see? The same as a pair of shoes. Shoes and the quantum world share many similarities. You can't just walk into a store and choose sneakers that perfectly fit your feet. Instead, you are compelled to select from predetermined size pairs. Similarity exists in the subatomic world. For demonstrating that energy can be quantified, Albert Einstein won the Nobel Prize. Quantum physics gets its name from the fact that energy can only be purchased in multiples of the same quanta, just like shoes can only be purchased in half-size increments. The Planck constant, after the pioneer of quantum physics Max Planck, is the subject of this quanta. He was attempting to apply our understanding of hot objects like the sun to a problem. The energy they release could not be explained by any of our best hypotheses. He was able to align the experiment and theory precisely by arguing that energy is quantized. 2. Particles and waves can both exist in the same thing. An electric sail, light, like wind on Earth, exerts pressure in space. In 1906, J. Thomson was awarded the Nobel Prize for his finding that electrons are particles. However, George, his son, was awarded the 1937 Nobel Prize for demonstrating that electrons are waves. Who got it right? Both of them are the solution. The fundamental concept of quantum physics is known as the wave-particle duality. It applies to electrons as well as light. Light can be better understood when viewed in terms of photon-shaped particles, but at other times it is more useful to think of it as an electromagnetic wave. A telescope is also a giant light bucket for collecting photons and can focus light waves from distant stars. As photons collide with an object, it also indicates that light can cause pressure. According to Rusty Schweickart, chairman of the B612 Foundation, this is something that we already use to propel spacecraft with solar sails, and it may be possible to use it to steer a dangerous asteroid away from a collision course with Earth. 3. Two locations can hold objects at the same time. The concept of a cat in a box was used by Erwin Schrödinger to simplify superposition. Superposition can be seen in wave-particle duality, for instance. Specifically, a quantum object that is simultaneously in multiple states. An electron, for instance, is simultaneously here and there. Only after conducting an experiment to determine its location does it settle into one or the other. Quantum physics is all about probabilities because of this. After looking at an object, we are unable to determine its most likely state. The wave function is a mathematical entity that contains these odds. The wave function is said to collapse when an observation is made. This means that the superposition is destroyed and the object is forced into only one of its many possible states. The famous Schrödinger's cat experiment is based on this idea. A quantum device is connected to the fate of a cat kept in a sealed box. The cat is simultaneously alive and dead until we look, just as the device exists in both states until a measurement is taken. 4. It may eventually lead us to a multiverse. We might just be one of many bubbles, each containing a unique version of the universe. Worlds within worlds within. The Copenhagen interpretation of quantum physics holds that observation forces a quantum choice and collapses the wave function. However, it is not the only choice that exists. The many worlds interpretation contends that there is no choice at all involved. Instead, when the measurement is taken, reality splits into two different versions of itself, one in which we witness the development of outcome B, and another in which we experience outcome A. It solves the difficult question of whether a dog or a robot can act as an observer and make things happen. Quantum particles, on the other hand, are limited to a single bizarre reality made up of numerous entangled layers. These layers untangle into the theory of the many worlds as we move closer to the larger scales we encounter on a daily basis. This process is known as decoherence by physicists. 5. It aids in the description of stars. The spectra of stars can tell us what elements they contain, which can help us determine their age and other characteristics. The spectra of stars can also tell us what characteristics they have. Niels Bohr, a Danish physicist, demonstrated that quantized electron orbits exist within atoms as well. Energy levels are their predetermined sizes. Photons have an energy that is proportional to the gap size when an electron shifts from a higher energy level to a lower energy level. Equally, an electron can jump to a higher energy level by absorbing a light particle and utilizing its energy. This effect is utilized frequently by astronomers. When we divide their light into a spectrum that looks like a rainbow, we can see colors that are missing, so we know what stars are made of. Because different chemical elements have different energy level spacings, we can figure out what the sun and other stars are made of by looking at the specific colors that are missing. 6. The sun would not shine without it. You'll just have to take our word for it that this is a picture of quantum tunneling. Quantum tunneling is the limited possibility that a particle can break through an energy barrier. Nuclear fusion is how the sun generates its own energy. It involves the adhesion of two protons, the positively charged particles that make up an atom. However, they repel one another due to their identical charges, similar to two magnets' north poles. This is referred to by physicists as the Coulomb barrier, and it acts as a barrier between the two protons. Consider protons to be particles that simply collide with the wall and separate. Sunlight and fusion are absent. But if you think of them as waves, the situation is different. The leading edge of the wave has already passed through the wall when its crest reaches it. The most likely location of the proton is shown by the wave's height. Therefore, although it is unlikely to be at the leading edge, it occasionally is there. Fusion takes place as though the proton has burrowed through the barrier. This effect is known as quantum tunneling by physicists. 7. It prevents the collapse of dead stars. It is hypothesized that the cores of white dwarfs may crystallize over time. Our star will eventually die as a result of the end of fusion in the sun. The sun will collapse, but not forever, as gravity prevails. There is more material packed into a smaller space. The Pauli exclusion principle, a quantum physics rule, eventually comes into play. This indicates that electrons and other types of particles cannot coexist in the same quantum state. Degeneracy pressure is a resistance that astronomers call gravity's attempt to accomplish this. A new white dwarf, or object of Earth's size, emerges after the collapse stops. However, degeneracy pressure can only withstand so much resistance. A fusion wave that shatters a white dwarf occurs when it grows to a mass approaching 1.4 suns. This explosion, which is bright enough to outshine an entire galaxy, is known as a type Ya supernova. 8. It causes the extinction of black holes. Some matter escapes from a black hole, even though not all that falls into it goes away. The Heisenberg uncertainty principle states that it is impossible to perfectly know two system properties at the same time. The accuracy with which you know one is greater than that with which you know the other. This applies to momentum, position, energy, and time separately. It's similar to getting a loan. You can borrow a lot of money for a short time or just a little for a longer period of time. We now have virtual particles as a result. A pair of particles can appear briefly if enough energy is borrowed from nature, and they quickly vanish to avoid defaulting on the loan. This process, according to Stephen Hawking, takes place at the boundary of a black hole, where one particle escapes, as Hawking radiation, while the other is swallowed. Because it is not repaying the entire amount that it has borrowed, the black hole slowly disappears over time. 9. It clarifies the vast structure of the universe. The universe has been expanding for 13.8 billion years, beginning as a singularity. The Big Bang is the best explanation for how the universe started. However, in the 1980s, it was altered to incorporate an additional theory known as inflation. The universe grew to about the size of a grapefruit in the first trillionth of a trillionth of a trillionth of a second, from being smaller than an atom. That is an incredible 1078 times larger. A red blood cell would be larger than the entire observable universe if it were inflated by the same amount. Quantum fluctuations governed by the Heisenberg uncertainty principle would have dominated the early universe because it was smaller than an atom. The universe expanded rapidly as a result of inflation before these fluctuations had a chance to disappear. Astronomers believe that this seeded the formation of the clusters of galaxies we see today by concentrating energy in certain regions rather than others. 10. More than a little spooky about it. Through the process of quantum entanglement, the properties of a particle can be teleported. Einstein argued in favor of another effect, which he referred to as spooky action at distance, in addition to contributing to the demonstration that light is quantum. Despite our current knowledge of the existence of this quantum entanglement, we are still unable to fully comprehend its nature. Let's say we connect two particles in such a way that their quantum states become entangled, or bound inexorably. The first is in state A, while the second is in state B. They can't both be in the same state, according to the Pauli exclusion principle. The other immediately adjusts to the change in one to compensate. Even if we separate the two particles on opposite sides of the universe, this still occurs.